Hi everyone, so this is Unit 4, Lesson 2, quadratic relations of the form y equals a times x minus h squared plus k. Sometimes we call this form vertex form, so you can also think of this lesson as being quadratic relations of vertex form. Okay, so this is a fairly long lesson. We have a fair bit to get through, so let's just get to it. We have something called a, k, and h, which we see here. These things are all called parameters, so you need to know what effects these parameters have. You're going to have to figure out the characteristics of a quadratic relation from its equation. So if I give you its equation, can you tell me some things about it, including its vertex, its axis of symmetry, and all that stuff from the previous lesson? And graph quadratic relations given their equations, and determine the equation of quadratic relation given its graph. So if I give you an equation, can you graph it? And if I give you the graph, can you tell me the equation? So basically, are you able to go in those directions? So graph given equations. If I give you the equation, can you graph it? Okay, so recall that when you have a quadratic relation, when you graph it, you make something called a parabola. And every parabola possible can be represented in some variation of this form, with some a, some h, and some k. So your most basic parabola is y equals x squared. And so I have it here on Desmos. Let's have a look. So on Desmos there, you can see that we have y equals to x squared. It's a basic parabola with the vertex at the origin. Hopefully you're probably familiar with that. Okay, so every other parabola where it's maybe moved over to the left or to the right or up or down, or it's stretched or it's compressed or whatever, all of those can be written in some variation of this. So a, h, and k are referred to as parameters. They will affect or transform the shape of your graph. So our first learning goal today will be to see if you can figure out the effects that each of these parameters has on the graph on your own. So as I say here, please take the time to do this. You'll learn better if you figure it out. You will understand it better because move up, move down, these terms are like kind of vague. So if you actually do it, you'll see specifically what they mean. So I have some questions for you to answer here. So I'd ask that you, if you're just watching this now, please try these questions out. So pause the video, see if you can do this activity, and then restart the video and I will give you the answers. Okay, so pause the video now. Okay, so I'm going to assume that you have done this activity, and I'm going to start going over the answers with you. So the first thing we're going to look at is the parameter k. So k is the term here that is outside of the square. So k is not in brackets and not squared. It's plus or it's minus, and it's after everything else. So you can see here I have simple equation, just y equals x squared, and I have only a k. So I don't have any a's or h's or anything like that added in here. Technically my a is equal to 1, but I've got like the basic a that I always have. So this is sort of, I'm only changing k here. So what is that going to do to the graph? Well, if we go to Desmos, let's put those two graphs on. So you can see here, there's my original graph. If I have a k of plus 1, that's what that looks like. So you can see that every point on the graph has been moved up by 1. So the vertex has been moved up by 1, but not only that, this point has been moved up by 1. Every point on the graph, no matter where it is, has been moved up by 1, and that's how you get from the red graph to the blue graph. Similarly, if I look at this graph here, you can see that that's now below my original graph, and it's down by 1. So if this is a negative number, then you get moved down by that number. And by moving down, what I mean is every point moves down by 1. So you can take all the points on this graph and subtract 1 from y. So you have the point 0, 0 on this graph. Subtract 1 from y, and you get 0, negative 1, which will be the transformation here. Okay, so we call this transformation a vertical translation. So let's write all that stuff down. So when k is positive, the graph moves up by k units. So if k is 3, it moves up by 3 units. If k is 4, it moves up by 4 units. it's negative, it moves down by k units. But I want to be specific again. Moves down is kind of vague, so the word that we have that specifically means all the points have gone up or down by k, or at least all the y coordinates have gone up or down by k, we call that vertical translation. So we can conclude that k is responsible for vertical translations up or down by k units. I don't really need up or down in there, I guess, because I've said vertical, that implies that, but there we go. Okay, now we're going to look at h, which is inside the bracket, so it's under the exponent. So first you would do h. If you know what x is, you first do h before you apply the exponent. Okay, so again, we have three equations here. I've taken out the k so that we can see the effect of h by itself. Okay, so I'm going to leave my base graph here, y equals x squared, on, and I'm going to put the other two on that I have there. So if I have an h of -1, you can see that the graph moves over to the right by 1. Okay, so it's kind of the reverse. So if you see -1 in here, that means you're going to the right. You might think that because this is the positive section of the graph, that you would have +1 going to the right. It's actually the reverse. You're going to learn more about why that is in grade 11. You might be able to figure it out on your own. I don't really want to get too wrapped up in that right now because you have enough to do already. So essentially we say usually that h is in here, so we have this normally written in the equation as x minus h. Let me show you that. So in the original equation we have it as x minus h, and this is where things get confusing. So if h is equal to +1, okay, if h is equal to +1, if you sub +1 in there, you're going to get x minus 1. Okay, so if you have x minus 1, your h value is actually positive. Similarly, if your h value was negative, if your h value was -2, if you put -2 in there, you would get x minus -2, which would become x plus 2. So if you see x plus 2 in there, your h is actually -2. So remember that this sign is reversed. So your h will have the opposite sign of what's in there, and the direction that the graph moves will also be opposite of this. So if h is 1, then you'll see that as x minus 1, and the graph will move to the right. Okay, that's a bit confusing. Takes some getting used to. Okay, so again, if we have a -1 in there, so we have x minus 1, h is 1, x minus 1, then every x coordinate gets moved over to the right by 1. Okay, so again, we don't just say it moves right, but every x coordinate on your original graph is moved to the right by 1 to generate your new graph. Similarly, if you have x plus 1, this is an h value of -1, and that means the graph now moves to the left. So if you have an h value of -1, this becomes x plus 1, and the graph moves by 1 units to the left. And so that means every coordinate on your original graph moves to the left by 1. So you have essentially every x value goes down by 1. Okay, so let's write that out. So when h is positive, the graph moves to the right, because remember we have x minus h. So when h is negative, the graph moves left. So we have x minus h. So again, remember, the reason I'm writing this x minus h is because you might think, oh, okay, when h is positive, the graph moves right. So that's this case here. But no, that's actually this case, right? Remember that when h is positive, we have x minus h. So if h is positive, then it will look like this. If h is negative, then it will look like this. So if the graph moves right, here the graph moves left. Okay, so we can conclude that h is responsible for horizontal translations of the graph by h units. Okay, so moving left and right by h units. Okay, and you might again say, well, why am I saying don't just say moves right or don't just say moves left? This word translation, the reason we use this word, this specifically means pick up every point and move that point to the left or right. right? When you say moves left or right, it's a little bit confusing because think about it. If I tell you to move left or I tell you to move right, well, you could step to the left, you could step to the right, you could kind of bend left or you could bend right. So move's a little vague. So when we say translation, that means everything, every part of the graph moves to the left by however that many units are. Okay. All right, so we have vertical translations by k units, we have horizontal translations by h units, and remember that h is your value for h is opposite whatever the sign is in here. What about a values? Okay, so in these graphs, I've gotten rid of any h and any k, so we can just isolate the effect of a and make it easier to see. So let's get rid of that. A values. So we have our original graph on here. What if my a value is 2? Well, then the graph gets stretched. Okay, so you can think of if you have like an elastic band or something like that. If you stretch it, then you'll go from this red part to this black part. So essentially it means that your graph goes up and down faster. Okay, but it's not just like, because of the way quadratic relations work, it's not just simply saying that, okay, well, if that's a 2, then every point is higher by 2. No, it doesn't really work like that. This is multiplied. It's not added. So you'll notice that the gap between the two functions is relatively small here. Sorry, that's a grade 11 term. You might hear me say functions instead of relations sometimes, but I'm basically meaning relations. The gap between these here is small, but over here it starts to get larger. Okay, so you've stretched the graph. You've kind of pulled it up. If this value is a number that's bigger than 1. What if it's a number that's less than 1? Well, then we flatten it. Okay, we compress it. The word that we use is compress. So again, you're not moving everything down by a certain amount. You can see that the gap here is quite large. The gap here is quite small. But instead, you're doing the opposite of stretching it. So instead of your graph being pulled kind of tighter, so to speak, it's kind of let to hang looser, if you imagine it as an elastic band. All right, what if our a value is negative? Okay, so then the graph flips over. So we call this a reflection in the x-axis, because the x-axis kind of acts like a mirror. So it's like a mirror image on this side. So to summarize, right, a negative a value will reflect the graph. A positive a value that is bigger than 1 will stretch it. A positive a value that is a fraction and is less than 1 will compress it. And that also applies if you have negatives. So you can have stretches and compressions combined with this negative as well. So for example, if I put a 2 in there, that will make it stretched and reflected. So a covers 2 characteristics of a graph. It determines if the graph is reflected in the x-axis, and it determines if the graph is stretched or compressed. Okay, so let's fill this in. When a is a number larger than 1, the graph stretches by a factor of a. So you'll hear it said that way sometimes, stretches by a factor of a. What does that mean? Well, factor means multiplied. So you're multiplying the coordinates by a, and so that stretches them out. Specifically, you're multiplying the x coordinate. Well, you're multiplying this part of it here by a. I'm not going to get into x or y yet. That's more of a grade 11 thing. But you're multiplying this whole thing by a, but not the thing on the outside. Okay, so it's a multiplication, so it stretches by a factor of a. Okay, what if you have a fraction that's less than 1? Then the graph compresses by a factor of a. Okay, so again, that's going to be a fraction. So if it's half, we would say that the graph has been compressed by a factor of half. Okay, and when a is a negative number, the graph reflects in the x-axis. I can guarantee you that whether we're talking about tests or exams or whatever, you are going to have questions that ask you to write out these transformations in English. So please do consider the vocabulary used here. The more precise you are with your vocabulary, the better your mark will be. Okay. Last sort of thing for you to investigate here that I'm going to take up with you is what if you have multiple transformations at once? So this, you can see I have a negative a, I have an h here of positive 1, and I have a k here of positive 1. So again, I didn't make a mistake there. When I said positive 1, Remember, the sign is opposite here. How will this graph be transformed? Well, let's see. This one here. So you can see that what I'm trying to show you here is that when you combine all these transformations at once, you can look at them all individually. So yes, this graph has had a few things done to it, but you can see that they can all be applied one by one and you won't get the wrong answer. So it's not like some weird combination that messes everything up. If you apply everything one by one, step by step, you can understand the transformation. So negative. So first, the graph is reflected in the y-axis. So it used to be like this, and now it's upside down. Then we can see that the graph has been moved to the right by 1. So the vertex, which was here, has been moved to the right by 1, and it's moved up by 1. So the graph has been reflected, then it moves left by 1, then it moves up by 1. One other thing to know here, you apply the A transformations before you apply the H and the K transformation. Because you're multiplying. So multiplying will come first. Technically, it doesn't really matter in terms of H, but you must apply A before you apply K. So say that you have the reflection before you say it moves up by 1. Okay. Again, you'll get into more of why that is in grade 11 when we add one more parameter to what it is you're trying to learn here. Okay. So let's just fill that one in. How has this graph been transformed? Okay, so it's been reflected in the x-axis. It's had a vertical translation, or sorry, we'll say, it doesn't really matter, but I'll say horizontal translation first. Translation to the right by 1 unit, and a vertical translation up by 1 unit. Okay, so let me make sure I got that right. So reflected in the x-axis, moved to the right by 1, moved up by 1. Again, using the vocabulary here. Is that what I have? Reflected in the x, moved to the right by 1, moved up by 1. Yes. Okay. So that's all the answers. So let's move on then. Hopefully you were able to follow along with all of that. So we're going to do some examples from your textbook here. All right, so first thing we're going to do is describe the properties of parabola with the equation 2 times x minus 4 squared minus 3. Sketch it, set the values that x may take and what values might y take. So in other words, you might have heard the terms domain and range before. I don't know if you have, but what values of x are allowed in this equation and what values of y are allowed in this equation. Okay, so sketch a graph. So we can have our parameters here. A will equal to 2, right, because it's there. H will equal to 4. So again, not negative 4, but positive 4. Sign is opposite. And K will equal to negative 3. So we have that there. So if we have 4 and negative 3, 4 is how much every point has moved to the right, and negative 3 is how much every point has moved down. So if your vertex has moved 4 to the right and 3 down, and it starts normally at 0, 0, that will mean that this is the vertex. Okay, so your vertex is always at HK. So if you have something in vertex form, the reason we call it vertex form is because you can just look at it and see what the vertex is. So it's 4, negative 3. We know it's going to be a minimum point because the graph opens up. There's no reflection here, so it doesn't open down, it opens up. It's U-shaped. Okay, and we know because there's a 2 here that there's a stretch factor of 2. Okay, and the equation of the axis of symmetry is x equals 4. Remember that your axis of symmetry always goes through your h coordinate, the x coordinate here rather. So your axis of symmetry is just always x is equal to h. So in this case, x is equal to 4. All right, so if we were to sketch that out, 4 comma negative 3, you can plot that on a graph pretty easily. So that's 4, that's negative 3. There we go. If I was going to do this by hand, I'd probably want to find another couple of points. That's pretty easy to do. So if you have a vertex at 4, negative 3, I might find a point at maybe 5 and negative 5, and you should find that if you find a point at 5 and negative 5, both of those points should have the same y value because these graphs are symmetrical. So you could plot a couple more points and then just trace it out. Okay, so the graph shows that x may be any real number. What does that mean? Well, it means that you can plug in any x value you want into the equation, and it will work. So you can kind of just see that if you have this equation, right? There's no like dividing by 0, there's no square roots, there's nothing weird in here. So you can plug in any x you want. You can plug in 1, 2, negative 7, pi, 15, root 2, whatever you want. X can go in there. And we can tell that that's true by graph because it goes to the right forever, it goes to the left forever, and there's no gaps in it. So yeah, x can be anything. So x can be any real number. Real number meaning a number that's not an imaginary or complex number, which you will worry about in future courses. Okay, what about y? Y is different. Y has to be greater than or equal to negative 3. And you can see that on the graph very easily, right? Because negative 3 is the lowest point. So you're never going to have a y value of negative 4. Right? The lowest it goes is negative 3. It's maybe a little harder to see that on the actual equation itself. So don't try to get it from the equation. Try to make sure that you're visualizing it from the graph. So y has to be bigger than negative 3. And that makes sense because essentially if you're going to try to solve this in reverse, if I have an x in there and my y is negative 3, when this 3 comes over, they will cancel and give me 0. And I divide by 2 and I still have 0. Then I have to take a square root. Right? If I'm trying to find x by itself, I will eventually have to take a square root. So this side can't be negative. And so negative 3 is the lowest it can be. Right? If it's negative 3, this 3 comes over and cancels it out exactly. If it's negative 4, this 3 will come over and I'll still have negative 1 left. I'll have a negative number. So I can't take the square root of a negative number and get another real number. So y has to be greater than or equal to negative 3. Again, if that's confusing, just look at the graph. It's really easy if you look at the graph. All right. So we figured all that out, I think. Yep, we've got all the characteristics we need there. So let's determine an equation for this parabola here. Write an equation for this parabola. So we know the equation is going to take the form y equals ax minus h squared plus k. You just know that, right? That's the form that parabolas can take. So what information do we have? We have a vertex and we have another point. That's always going to be enough to give us an equation. If you have a vertex and another point, you've got it. If you have a vertex, think vertex form. This is h and this is k, right? That's how the vertex works. This is h and this is k. This graph has been moved over to the right by 1 and it's been moved up by 5. So that's where the vertex was originally, and when we transformed it, we moved the vertex over by 1, up by 5. So that's your hk. Okay? So you can basically sub those into the equation. So your h is 1, your k is 5. Again, remembering that sign here, this is x minus h. So if h is positive 1, then you get x minus 1. K is 5. But we don't have a. So how do we get a? Well, it's actually not that hard. That's where the other point comes in. So you have an x value of 0 when you have a y value of 2. So just like when you're trying to solve for b in a linear equation, you sub in m, x, and y. Here you're trying to solve for a, and the only thing left to sub in is x and y. So you'll sub in the point. So if the point is 0, 2, x is 0, y is 2, you'll notice the only thing you have left is a. So you can solve for it. Okay, so 0 minus 1 is negative 1. Negative 1 squared, remember that if it's in a bracket like this, this means negative 1 times negative 1, so that'll give you positive 1. So we have positive 1a. We bring the 5 over to the other side, and we get our a value equal to negative 3. So now we have h, we have k, we have a. We plug them all in, and we have our finished equation. Okay, so hopefully that's not too hard. All right, next question here, fireworks. All right, you are going to have some word problems here. So at a fireworks display, a firework is launched from a height of 2 meters above ground and reaches a maximum height of 40 meters at a horizontal distance of 10. All right, so I would definitely sketch this. If I was doing this as a word problem, I would definitely want to sketch this out. So we have a sketch there. Horizontal distance of 10, height of 40. And we want to model the flight path of the firework. So specifically what we want to look at is how does its height compare to its distance. So as the firework kind of travels, we're tracking its height and its distance. So this is actually the path of the firework that it travels. Okay, so it's got a maximum height of 40 and a horizontal distance of 10. So you move 10 on the x-axis and up 40. So that's where the firework reaches its highest point. So we know that's going to be the vertex, right? Because that's where it turns around. And it's launched from a height of 2 meters. So we typically would have the firework launch from location 0 because that's just easiest. And its height is initially 2 meters. So when it hasn't traveled any horizontal distance before you've launched it, it's 2 meters above the ground, maybe on some kind of platform or something. All right, so we have this picture here. It looks something like that. Determine an equation to model the flight path of the firework. Okay, so hopefully you'll notice this looks just like the question we just did, right? You have a vertex, you have an H, you have a K, and you have a point on the graph that's not the vertex. So you're going to be able to plug that point in and solve for A. So that's all they do here, right? 10, 40, H, K, you plug that into the equation. You substitute the point 0, 2 in for Y and X, and then you just solve for A. Okay, so typically in a real world problem, you're not going to get nice numbers, and you don't in this case, although that's not too bad, right? At least that's a terminating decimal. So your A value is negative 0.38. So then you can just simply plug in A, H, and K and figure out your equation. Okay, so again, this word problem have a therefore statement, but I'm not going to go through all the steps to that because it's just the same as what we just did in this question. Part B. The firework continues to travel an additional 1 meter horizontally after it reaches its maximum height before it explodes. What is the height when it explodes? Okay, so what is this saying? Well, this is saying that the firework reaches its maximum height, but it actually doesn't blow up here, right? It keeps traveling for another meter, so it starts to fall, and after it travels another meter horizontally, so after you go this way another meter, it blows up. So it's going to blow up somewhere here. Okay, so we want to know what is the height when it explodes. So it's going to be lower than 40, but we don't know exactly how high. All right, so how do we do that? Well, we already have the equation, right? We have y equals negative 0.38 x minus 10 squared plus 40. So what we're trying to find is the height. We're trying to find y. So y is easy to find if you have x. And it turns out that actually we already have x because it says that we've traveled 1 meter horizontally after reaching its maximum height. Its horizontal distance at its maximum height is 10. So if you move 1 meter over, you're at 11. So the x value where it blows up is 11, and we can just sub that into our equation. So x equals 11. We just put that in there. Again, we have our A, we have our H, we have our K, and that's it. That's all you got to do because that's going to let you solve for y. So remember, brackets first. 11 minus 10 is 1. 1 squared is just 1. So that's still going to be negative 0.38 plus 40. And so when you add those two numbers together, you get 39.62. So the firework explodes at a height of 39.62 meters. Okay, that's it. That's a simple question. All right, last part. At what horizontal distance is the firework the same height as in part B? Okay, this is maybe a little confusing here. What is this trying to ask? It's a simple question, but it's worded maybe a little confusingly. So it's saying that I was reading this wrong, by the way, so I had like this as 1. This is not 1. This graph is going up by 5s. So if you move over by 1, you're probably more actually here. So the firework will explode somewhere here. So if your maximum height is 10, you move to the right by 1. You're at 11, 39 point, what was it? 39.62. Okay, so this question is saying, where else are you at 39.62? So this is basically just getting you to think about the symmetry of parabolas. So if you're at 39.62 here, you would also be on the other side at 39.62. The axis of symmetry runs through the vertex. So this is saying if you go to the right by 1, so from 10, if you go from 10 to 11, then you're going to be at 39.62. So if you go 1 to the right of 10, you're at 39.62. So the same should be true if you go the other way. So if you go 1 to the left of 10, then your height should be the same, 39.62. So if 10 plus 1 is 11, 10 minus 1 is 9. So the other horizontal distance is 9. You don't even have to do any calculations, really, other than 10 minus 1. You just have to understand how the symmetry works. Okay, so due to the symmetric property of a parabola, the firework is the same height 1 meters before the maximum point, or at a horizontal distance of 9 meters. Okay, so I've posted this from your textbook in here as well. This is just a summary of the terminology. We've covered most of this stuff already. Values x may take and values y may take is a new concept, at least as far as this class is concerned. We've said that this is sometimes called domain and this is sometimes called range, so you might be familiar with those terms. And that's all we have to cover here. All right, thank you.